Hey y'all, so today I know we ended class trying to figure out this problem and I paused a little bit. Turns out I'm human, but I ended up finding out the error right after class, so of course that's life. But just wanted to give you all the answer. So remember that we were trying to maximize the function f of x comma y equals x squared minus y squared subject to the constraint x squared equals 2y. Now I know that's a little bit small of writing, so don't worry, I'm going to kind of write bigger. Now we have that whole process that we kind of laid out in class as far as how to maximize when given a constraint. And yet again, we'll get into the details of that on Wednesday. But step one was to come up with the constraint function. All that was manipulating this guy to get one side equal to 0. Well, if we subtract over the 2y, we all of a sudden have our constraint function. Just x squared minus 2y. And what we go ahead and call that is the function g of x comma y. Now step two in the process was to come up with the big function where we get the lambda involved, the capital F, the Lagrangian function. Now remember that this is a function of 3 variables, we're including lambda, and it's defined as our original function minus lambda times your constraint function. Now just plugging into place what we get, well, f of x comma y was x squared minus y squared minus lambda times our constraint function x squared minus 2y, which simplifies out to be x squared minus y squared minus x squared lambda plus 2y lambda. And that's the function that we're going to be working with. Now I have a limited whiteboard, so if you don't mind. And of course it's not going to erase either. Step 3 is going to be find our partial derivatives of this guy. So recall that this was my function f of x comma y comma lambda, capital F. Step 3 said find the partials. Capital F sub x, well, derive this guy with respect to x, and we got a 2x. These terms will become 0 because there's no x. And last but not least, this term will become a minus 2x times lambda. F sub y is somewhat similar. These two terms do not have a y, so they become 0. But this term right here will derive to be negative 2y. This term right here will be plus 2 lambda. Last but not least, deriving with respect to lambda, neither of these have lambda in it. These guys do. We just get our constraint function back. X squared, negative x squared, excuse me, plus 2y. Make that a little bit more obvious. That's ultimately what our system of equations is going to look like. And now, to complete step 3, what we end up doing is solving this system of equations where each of these equals 0. Well, we're actually going to proceed somewhat similar to how we did in class. From this equation, what I can gather, adding the 2y over, is that 2 lambda equals 2y, or, ultimately, lambda equals y. Now I'm going to take that, I'm going to put that in my back pocket. That's going to be important. Now what can I gather from this equation right here? Well, we kind of had a mix, and this is where we ran into issues. However, what we should do is our original approach of factoring out the 2x. From this guy, what I can get is that 2x, and then factor it out will leave me with a 1 minus lambda on the inside, equals 0. I apologize for the shaking. Turns out my cat's in the frame. He can help. Alright, Ollie, you're helping. Whenever I have two variables equal to 0, what I do with that is I set each equal to 0. And that gives me two possibilities. So either 2x equals 0 or 1 minus lambda equals 0. Here, you can help me erase. Well, in the first case, either x equals 0, or in the second case, lambda equals 1. All right, someone's not happy. Well, from each of these cases, we actually have to solve... Ollie, stop it. No, sir. We actually have to solve both of them out. So case number 1. I should say case A since I'm already using numbers. Case A, let's pursue what happens when x equals 0. Well, when x equals 0, from this equation right here, we can say that, well then 0 squared, negative 0 squared, plus 2y equals 0. Well, that just tells me y equals 0. But then from this equation right here, we have that lambda equals 0. That's my first set of solutions. Now my second set is actually somewhat similar to what happened in class. So case B was what if lambda equaled 1? Well, if lambda equals 1, all of a sudden, from this equation, that means y is equal to 1. But then ultimately what we can do is go ahead and plug in right down here to get what x equals. Negative x squared equals 2 times 1. Oh, excuse me. Negative x squared plus 2 equals 0. Which ultimately gives me, upon solving, x equals plus or minus the square root of 2. So take a moment, go ahead and pause and rewind if you have to, but that's what we end up getting from this whole thing. Two different solutions. Well, excuse me, 3 different solutions based on that outcome right there. Why either x was equal to 0 or lambda is equal to 1. Either could have happened. This actually constitutes 3 separate solutions. The solution from this is the order pair 0, 0, 0, where we have an x, a y, and a lambda term. This equation right here, or this system right here, gives me 2 solutions. Either we got positive square root of 2, 1, and 1, or we get negative square root of 2, 1, and 1. That's where we get those. Those are our 3 things that we have to test. But that concludes step 3. Step 4, which we did not get to in class, would say ultimately test your x and y coordinates in your original function. So all we do is evaluate little f of 0, 0, little f of square root of 2, 1, and little f of negative square root of 2 and 1. Now what we'll see from this guy, 0 squared minus 0 squared, we'll get a 0 here. Plugging in either of these guys, square root of 2 squared will give me positive 2, minus 1 squared, we'll just get positive 1. And in fact, we'll get the same thing down here. Since we're trying to maximize the function, we'll say that we have a max of z equals 1 occurring at the points square root of 2, 1 and negative square root of 2, 1. Chase, come here. Come here, come here, come here. So ultimately, hopefully that answers the question. This guy was getting a little jealous. So, with all due respect, hopefully that solves some stuff out. Chase is probably looking uncomfortable. Y'all have a good one.